Welcome to the third cycle of lectures on quantum mechanics. In this first lecture, we noticed that measurements at different times are related to each other by unitary transformations. Then we consider an infinitesimal time step and infer the equations of motion by Schrödinger and Heisenberg. So let's consider again a situation that we discussed before. We have a source that emits photons. The photons are vertically polarized. Then when they are measured by a Z measurement, all of them give us the value +1. And none of these photons goes to where we have the value -1. So all are here, none are there. Now, if instead of vertically polarized photons, we have horizontally polarized photons, then none of them go here, and all of them go there. And this is, of course, just a reminder that the Z operator has value +1 for the vertically polarized photons and value -1 for the horizontally polarized photons. Now, let's modify this experimental setup a little bit. So we have the source, the photons that are emitted from the source. Before they are measured, we send them through a wave plate. And this wave plate is such that it converts a vertically polarized photon into a photon that is diagonally polarized. And a horizontally polarized photon becomes an anti-diagonally polarized photon. Now, rather than measuring Z, we measure X. And again, we have outcomes +1 and -1. So, the diagonally polarized photons, they all go here, and none of them go there. And for the anti-diagonally polarized photons, it's the other way around. None of them are here, and all are found there. This, of course, is just saying again that the X measurement has value +1 for the diagonally polarized photons and value -1 for anti-diagonally polarized photons. Now let's look at the overall picture. If we measure the photons as they come out of the source, so we measure the Z at this early stage, then we get the values +1 and -1, plus for the vertically polarized photons, -1 for the horizontally polarized photons. However, if we put them through the wave plate and then measure X, we get +1 for the ones which are diagonal, -1 for the ones which are anti-diagonal. But the diagonal ones are those that start out vertical. The anti-diagonal ones are the ones that start out horizontal. So, for the ones which are vertically polarized as they come from the source, and they finally give +1 here, they also give +1 there. The ones that come horizontally polarized from the source, they give -1 there, but they also give -1 here. So, whether we measure Z at this early stage or we measure X at the late stage, these two measurements are the same. It's two different ways of telling whether photon that left the source was horizontally polarized or vertically polarized. We can either measure Z directly, or we can use a wave plate and an X measurement. We get the same information. So if we denote symbolically this early measurement as happening at the time t1 and this late measurement as happening at the time t2, we can see the Z measurement at time t1 is equal to the X measurement at time t2. So here we have a very elementary way of talking about measurements at different times, early and late, without, however, resolving what happens at intermediate times. So at an intermediate time t, say, while the photon is converted from vertical to diagonal, from horizontal to anti-diagonal inside the wave plate at an intermediate time, there should also be a state of affairs that is described by operators that refer to this time. So now let's talk about this situation of operators depending on time, because we can make a measurement now, we can make a measurement later, we can make a measurement today, we can make a measurement tomorrow, and these are different measurements. So when we have a generic operator, A, we used to write just a sum over the kets that are associated with this operator, the eigenvalues alpha k, and the bras that we get for this operator. Now, here there was no reference to time. But now let's be more specific and take into account that the measurements happen at a certain time. And so there will be a ket and a bra that refers to this particular time. But for now, I will assume that the eigenvalues are the same for different times, just like in the example that we discussed. There's the z measurement at one time, the x measurement at the other time, but the eigenvalues in both cases are plus and minus 1. So I don't want to give a time dependence to these alphas right now, but keep this option open for a later stage. So here we have the operator A at one time, and there's the kets at one time, the bras at one time. And then there's the operator A at a different time, say T1 and T2, where we have the same kind of structure, but we have a different set of bras and a different set of kets, because they will refer to different times. Now remember, if we have two bases, say the A basis referring to a quantity like this, and another basis bk that goes with a different observable, then we can convert the kets from one basis into the kets from another basis with the aid of a unitary operator that is of this form. So we have the AK ket combined with the BK bra. And now if I take this U and I apply it to a BK ket, I get the corresponding AK ket. And of course I can also take the U and apply it to the kth bra from the A basis, and I will get the kth bra from the BK basis. So this U is unitary, which means that if I take U multiply with its adjoint, I get the identity. Doesn't matter in which order this multiplication is done. So now coming back here, what is A and B over there could be the A basis at one time and the A basis at a different time. So there is a unitary relation for converting the A basis at one time to the A basis at a different time. Now, rather than looking at finite time steps from T1 to T2, we do what physicists like to do. We look at small time increments. So I'm asking, how is a bra at time t plus dt related to the bra at time t? Well, according to what we have here, this one bra, the other bra, different bases, there should be a unitary transformation here, but this unitary transformation should be almost the identity, because we are just going from t to a slightly later time dt. So what we need to write here is a unitary transformation such that it's not very much different, not very different from the identity. So I begin with the identity, then there is a small correction. That correction should be proportional to the dt, so there will be a dt here. And then there should be some operator that acts on this bra to convert it into a new bra. And now, using standard notation, this operator will be denoted by h. It will refer to the time t that we are talking about. And then there is also a factor of I and a division by h bar. Let me say a few words about this before we proceed. This operator here is the energy of the system. Now it's an operator. It goes with the name of Hamilton operator. Or, as some people prefer to call it, the Hamiltonian. The h bar that appears here is Planck's constant divided by 2 pi. So h bar is Planck's constant, for which we usually write h, divided by 2 pi. And that's a very small number, 1.0546, and more digits are known, 10 to minus 34 joule seconds. So joule and second are microscopic units, SI units. And h bar, in some sense, sets the scale for atomic units. And these atomic units are so much smaller than the macroscopic units that we should not be surprised to see a very small number here, a large negative power of 10. So joule is energy, as second stands for time, the product of energy and time. So it has the metrical dimensions of energy times time or action. And so h bar is what we call the quantum unit of action. Never mind the words, it involves energy and time, h for energy, dt for time. And so we have to divide by something which has the same metrical dimensions to get something that has no metrical dimensions, it's just a number. Now, why is there the I? Okay, the I is because this operation should be unitary, and so we have this prototype of a unitary operator that differs from the identity by a very small amount. So let me just write 1 minus I times an epsilon, a small amount. So then the adjoint of that is 1 plus I epsilon adjoint. I multiply the two, I get u times u adjoint equal to 1 times 1 is 1. The 1 times the plus I epsilon adjoint is I epsilon adjoint. The minus I epsilon times 1 is minus I epsilon. And then there is the term where the epsilon is multiplied with the epsilon adjoint, but this epsilon is an infinitesimal quantity, so we don't need to take its squares into account. And so if this is a unitary operator, so the product should be 1, we need the I times epsilon adjoint to cancel the minus I epsilon. So this combination needs to be 0, and that requires that the epsilon is equal to its adjoint. So the epsilon is Hermitian. And so this Hamilton operator is Hermitian. H is equal to its adjoint. And so that's something we want to have for the Hamilton operator because it corresponds to energy. Energy is a real quantity, so we should have an operator that has real eigenvalues. And so having a Hermitian operator is just fine over there. And so this is why we want to have the I here. So we have this statement that the kth bra from this basis associated with operator A at time t plus dt is the corresponding bra at time t multiplied by this operator, which is a unitary operator, but a unitary operator that differs only infinitesimally from the identity. And this infinitesimal deviation is measured by the time increment dt. Now, on the other hand, we can just recall what is the beginning of the Taylor expansion for such a function of t. So here we would have a k at time t plus dt times the time derivative of a k at time t. Okay, and then there are no higher order terms because the dt is infinitesimal. So, compare this expression with this expression, we can read off that the time derivative of the kth bra for operator A is equal to that same bra at time t, and then multiplied by negative I divided by h bar, the Hamilton operator at time t. Well, now, if we multiply by I and we multiply with h bar, then this factor goes away, and we have a factor of I and a factor of h bar on the left. Then the time derivative of akt equal to akt this bra, the Hamilton operator applied to it. Now, as we go to this analysis, we were talking about a particular physical property that we symbolize by A with its eigenvalues alpha k and its eigenkets and eigenbars labeled by A, K, and T, and so forth, right? But there is nothing particular about this observable A. We could have taken another observable B or a third observable C. We would always end up with the same statement, which is to say that this is more generally true than just for a particular A. So if I write this in a more general way, I write IH bar, the time derivative of a bra. Here are some quantum numbers that specify it, like this AK, and then that's the same as that bra at time t with the Hamilton operator applied to it. So this ellipsis here stands for any set of labels that identify the bra. It doesn't have to be AK as in this discussion. It could be a BK, it could be a CK, or it could be even several labels that identify the bra. Whatever they are, this is how the bra changes in time. And this very important statement is what is known as the Schrödinger equation. So it's more specifically the Schrödinger equation for bras. Here's the Schrödinger equation for bras, but there is also a corresponding equation for kets, which we get by taking the adjoint. So taking the adjoint on the left and the right hand side of this equation, we get negative IH bar, the time derivative of the ket, equals to h at t times the ket at time t. So this is the corresponding Schrödinger equation for kets. They are very similar, but they are not the same, right? So it's IH bar d by dt, ht over here. It's negative IH bar d dt, ht. And of course, since this is a bra, the Hamilton operator acts from the right. Since this is a ket, the Hamilton operator acts from the left. And in going from here to here, of course, we take into account that the Hamilton operator is its own adjoint. Okay? So we know how the kets and the bras change in this setup. But what does it say about the time derivative of A? Well, let's take a look. We take the time derivative of A, and there will be several contributions. One from the change of the ket, and one of the change of the bra. So let's just write this down. So for the ket, we look at the time derivative for the ket. So this will have negative 1 over IH bar, the Hamilton operator acting on the ket. And then when we differentiate the bra, the ket is unchanged. The alpha k doesn't depend on time. And now for the bra, we get the bra, and then it is 1 over IH bar, the Hamilton operator, acting from the right on the bra. But the summation does not affect this Hamilton operator factor here or there. So looking at the second one, we have the operator A at time t, and then 1 over IH bar, the Hamilton operator at time t. This is all of this second part. The first part looks similar. It's minus 1 over IH bar, the Hamilton operator at time t, then the operator A of t. So we can combine this into a more compact expression by writing 1 over IH bar, and then the so-called commutator of the operator with the Hamilton operator. So here we introduce a notation, the so-called commutator, of two operators A and B, and that's written as this A comma B in square brackets, and it just means the product of AB minus the product of BA. So here we have A times H minus H times A, and that's exactly this commutator structure. So this is not zero as a rule, because we know that when we multiply operators, the order matters. Order matters when multiplying. So therefore this is generally speaking not equal to zero. There's a real time derivative of this operator A. Alright, so for an operator of this kind, where the eigenvalues do not depend on time, this is the time derivative where we have the commutator, the operator with the Hamilton operator, and I remind you that this comes from first understanding the Schrödinger equation for the kets and the bras that appear in this structure. Now, let's also consider the more general case that the eigenvalues themselves depend on time. But this, we need to understand, is something of our choosing. So earlier in the lecture, we were talking about measuring the operators Z and X for polarized photons, but we gave them the numbers +1 and -1 at both times. Now imagine that for the Z in the early time, we use the numbers +1 and -1, but for the X at a later time, maybe we use +2 and -2. So that would be a change of this kind. And then there is an additional time dependence that we introduce by using different eigenvalues at different times. If we do that, and we can, that's an option, then there is clearly another term to this time derivative of A, and that additional term would just be the sum over k. So here is the AKT. Then there is the time derivative of this alpha k at t with respect to t, and then there is the bra AKT. So if we combine this, then we will see that the second term is a parametric time derivative of t, which comes because at different times we have different structures for this operator, because we, by our choosing, introduce a time dependence of the eigenvalues. And then there is the part of the time derivative which has to do with the dynamics of the system. So here is the commutator with A of t and the Hamilton operator. So we have two contributions to the time derivative of the operator. There is the parametric time dependence, and there is the dynamic time dependence. and they both together give us the total time dependence. So I repeat, this operator A of t depends on the dynamics of the system, which tell us how the cats and the brass at one time depend on those at an earlier time. And then there is a parametric time dependence of our choosing by deciding that we want to have, for one reason or another, time-dependent values for the eigenvalues. So there's this parametric time dependence, there's the dynamic time dependence, together that's the total time dependence. And what we have arrived at now is the Heisenberg equation of motion. So that's the equation of motion for an operator. The Schrödinger equations that we have seen before are, to begin with, equations that tell us the time dependence of brass and the time dependence of cats. In summary, there is the Schrödinger equation for the evolution of brass and the adjoint equation for cats and the Heisenberg equation of motion for operators. In the next lecture, we apply this to the time dependence of a qubit.